were not here Friday, we did the College Board assignment, the topic questions. It's due Friday, next Friday, this coming up Friday at 11:45 p.m. So, guys, when I do something online, I always make it 11:45 p.m. That's the latest time slot. So I give you the whole day. So just know that that's when it's due. If you finished it, then it's great, but it's due Friday. Also, we have kind of a weird week. We have a little bit longer notes today. You'll have time to work on your homework, but there's no new notes tomorrow. It's just practicing what we learned today because it's so important. Then we have a new lesson on Wednesday, which is 1.7. Guys, also Wednesday is one of those club days, the one big lunch time, so it's a different bell schedule on Wednesday. There's no school Friday. Okay, you guys don't have school Friday, but Thursday I won't even see you guys because that's when 9th and 10th graders are taking the FAST test, Exam 1, and juniors and seniors will be in the auditorium if you come to school. So 1st through 4th, you will not be going to any of your classes, so I will not see you on Thursday. Okay, they're kind of encouraging juniors and seniors to take college days that day. I don't know. It's up to you. I'm not telling you what to do. I'm saying you won't see your 1st through 4th teachers. And I don't think they're going to take attendance in the auditorium, to be quite honest with you. So you didn't hear that from me, though. Okay. So, guys, listen. You have new notes now. Shh. Please stop talking. You have new notes now in your binder, hopefully. Your old stuff, it's yours. I'm not going to tell you what to do with it. But I can tell you in the past, some people kept everything in their binder. They like to have everything right there. Some people took it out and left it at home and the desk under their bed. I don't know what you do with it. And some people throw it away. It's your prerogative. You do what you want to do. Just think maybe you might want to go back and look up something. So maybe save it somewhere, not in your binder, so you're not carrying it around. Our next test is on all of Unit 1, so everything in Unit 1 will be on that first test, but this is the second half of Unit 1 that I gave you, okay? What I would not get rid of, listen, is the test review that we just had last week, the blue, I think it was blue. You can count on me checking test reviews as a homework check. I always do. So you know at least that will get checked, so don't get rid of that, okay? Keep that in your binder, whether it's in the hole, in the thingies, the rings, or in a pocket. Make sure you have it. You know I'm going to check it, okay? But I won't go back to any other homeworks. Okay, so what we're doing today is mostly like Algebra 2 stuff. A lot of second period was like, yeah, I kind of remember this from Shackton or Springer, whoever you had. I'm going to reteach it to you, but it's all about end behavior. And we're bringing back like multiplicity and how graphs interact with an x-axis, so some things that we just learned. As far as the test goes, I should talk about that. It was just last week. If you did not finish it, some of you said you were coming back at lunch and did not. You'll finish it in class tomorrow, and like Bella, who didn't take it at all. If you were absent, you'll take it in class or finish it. And if you have not finished your test or taken it, you're taking it in class tomorrow. What I'm trying to say. Okay? This class, we didn't have any perfect scores, but the highest score was Hunter. Where's Hunter? Where's Hunter? I don't have my same chart. Where's Hunter? Oh, sorry, Hunter. Good job. 97. But right behind Hunter was Jacoby with a 96, Zoe with a 96, Solly with a 95, Carlos with a 93, Caden with a 92, Logan had an A. Those are my A's. So about a third of the class got A's. So far, I mean, there's like 5 people that still have to make it up. So now that you've had a feeling of how this class goes, we're just starting over again, basically. You have new notes. We have the notes, the homework checks periodically, all that stuff, okay? So we're now in this rhythm. Keep it going, okay? Because you guys are doing well. All right. Listen, by knowing the degree of a polynomial function, it is possible to predict the end behavior. End behavior of a graph is what the arrows are doing, okay? And we'll talk about that more in a second. Shh, please stop talking. So let's talk about this. There's a couple different ways we talk about end behavior. A lot of what you're doing today is either interpreting a graph into words or symbols, or words and symbols into a graph. It's really about being able to see and hear and write end behavior a couple different ways. So this phrase right here, the inputs increase without bound, okay? inputs are your x's, right? So anywhere we see something that has to do with inputs, that's your x's. Anything with outputs are y values, right? Just fancier word than x's, but that's what they are. And when the x values are getting bigger without bound, what that means is that it keeps going. It doesn't just stop without bound. Like nothing's stopping it from continuing to increase, okay? So what that means in English is that the x values are increasing without bound, are moving towards infinity, right? That's going to the right. Yeah. You don't have page 70?
Yeah, I have
Did anybody have an extra page 70 by chance? Because this happens every once in a while. It would probably, it would be at the very back. It would be your last page. Sorry, guys. Can you look at your last page? Oh, who did I see that? Oh. Thank you. That was my fault, nobody else's. Thanks, Connor. Sorry about that. Okay, back to what I was saying. I'm just going to draw a little coordinate for you here. So what we just talked about is x values moving towards infinity, and I'll keep the colors the same to kind of color code this. They're going to the right, right? That's our right behavior. That's what we're talking about right there on a graph, okay? The inputs decrease without bound. That means and I'm going to start abbreviating now. X values are moving towards, what do you think? They're decreasing. Negative infinity, right? That's our left behavior. So that's x values are going to the left. Okay? Outputs, y values increase without bound. Of course, now we can kind of start scooping through these. Y values moving, so increasing, moving up, that's towards infinity. Right? That's these guys right here. That's going up. And decreasing, that's down, right? Y values moving towards negative infinity. Right? As you go to the right, you're going towards positive infinity. As you go up, you're going towards positive infinity, right? When you go down, you're going to negative infinity, and when you're going to the left, you're going towards negative infinity. That's stuff you already know, right? We're just kind of putting it in this language. All right? So, next page, please. So, when we talk about end behavior, there's two sides, left and right. We have left behavior and right behavior, okay? So end behavior of a function describes what the y values of a function are doing as the x values either increase or decrease, okay? So left end behavior of a function describes what the output values of a function are doing as the input values decrease. That's the left end, right? Think back to that picture. As we go to the left, the x values are decreasing. Okay, so that's the left side of the graph. The right end behavior function describes what the output values, the y values, are doing as the input values increase. That's going to the right, right? As you go to the right, the x values are getting bigger. Visually, this is the right side of the graph. Okay, so let's look at a specific graph. The graph at the right is called g of x. Let's answer some questions. As the input values, that's your x's, increase without bound, what are the output values doing? So this is looking simply at the right side of the graph, and really all we care about is that arrow. That's it, okay? Nothing else matters. It's literally, like, you don't even care what the graph is doing as it gets to it. It's what is this arrow doing? So in a polynomial, it almost looks like we're going straight up and down, but we're not, okay, ever. We're tilting a little bit. Like this part of the graph is going towards the right, right? Our x's are increasing on the right side. are the y values increasing or decreasing? Increasing. If you're going up, you're increasing. So our y output values or y values are increasing without bound. That just simply means there's an arrow. It goes on forever. Nothing's going to stop it. No boundary to block it. Okay? As the input values decrease, that's our left side. The input values decrease is left, increase is right. What are the output values doing? So again, all we care about is this arrow right here. That's all we care about. What is it doing? Well, it's definitely going to the left, right? It's going to the left a little bit. So the x values are getting smaller. Are the y values increasing or decreasing? Decreasing. It's going down. Decrease without bound. Okay? So here's a new symbol that you need to know. Like, you've learned tons of symbols in all your years of math. Like, back to a plus sign, right? And you know when you see a plus sign, it tells you to do something. Parentheses, powers, all the different things that you see. Here's a new one, and this is from calculus. This is an arrow going like that, and it means approaches. Like, you literally say the word approaches when you see this symbol. And I'll show you what that looks like here in a second. So here's 3 different ways that we can say some of our end behavior. So out loud, verbally, as x approaches either infinity or negative infinity, depending on if it's going to the right or to the left. So as x approaches infinity or negative infinity, f of x, remember, f of x are your y values. Sometimes it might say outputs or something like that. F of x approaches either infinity or negative infinity. Infinity would be going up, negative infinity would be going down. Symbolically, here's that symbol. As x approaches either infinity or negative infinity, right, or left, f of x approaches either infinity or negative infinity. So whether it's going up or down. Okay? And finally, here is something called limit notation. This is your first, I'm guessing, first introduction to limit notation. Notation means a way we write something, and it involves something called limits that you'll explore when you get to calculus. Limits is the very first thing you learn in calculus. We don't do limits in here, but we do limit notation. So it's kind of nice in this course that you learn how to do this stuff, and then it makes that limit learning later a lot easier. It looks complicated. I promise you it's not. It's very, very simple, okay? It's not something I ever take points off of on a test because no one ever gets it wrong, okay? But there is a proper way to write it. So let me show you what we're going to do. Using the graph above, we're going to fill in the following sentence and translate those sentences by using limit notation. So using this graph up here, it says we're going to look at the left side first, okay? So if we're going to the left, x is approaching which? Positive or negative infinity? When we go to the left. Negative. Right? When we go to the left, the x's are getting smaller, right? This is left. This is right. Okay, what are our y values doing here? They are going towards, the y values are approaching also negative infinity. We're going to the left and down. That's what that arrow is doing. Okay, let's do the right side. I'm sorry, you can't see what I'm writing. I'm sorry. I hate it when I do that. Yell at me politely, because I'll cry. Right end behavior. If it's saying to the right, x is going towards positive infinity. That's a terrible infinity symbol. Don't judge. But in the graph, what are our y values doing? As x gets bigger, so does y. So when y is getting bigger, we're approaching positive infinity. Okay? Now I'm going to teach you how to write limit notation. And there is an FRQ on the AP exam where you have to do limit notation, and I graded this question this summer, and I can tell you that we took points off left and right. I'm telling you there are teachers out in the world that are not teaching how to do this because it's so easy, all right? Let me show you. You actually write the letters LIM, which stand for limit. You don't write the word limit. If you write the word limit, it's wrong. It's supposed to be a very specific way. So LIM. You'll never write the whole word. LIM. Of whatever graph we're talking about. Okay, in this particular case, they called it g of x. Remember I said you always have to call a function by its name? Here's another example of that. The limit of g of x, and right under the word limit, as x approaches, and this is our left end behavior, so that would be negative infinity, right? Left is always going to be negative infinity. Equals negative infinity. So again, what you're seeing here, so as what you, let me just make it real simple here. What you are looking at is right here where the x is going, and over here it's what the y's are doing. X is going to the left, y's are going down, right? Left and down. Okay, let's do it for right end behavior. The limit of g of x as x approaches, and this is right end behavior, so I'm going to put positive infinity, equals, and then we're going up, that's positive infinity. So it's just another way of writing it. You might have done like arrows back in the day, which you'll see me do again. Like a quick way of describing your end behavior here would be down on the left, up on the right, right? That's end behavior. Just saying what the arrows are doing. Okay? All right, so we'll practice that more in a second. Here's an Algebra 2, straight out of Algebra 2 lesson for you, which is how do we tell what the end behavior of a graph is? How do we tell the end behavior of a graph is if it's not graphed? If we just have the function? Well, it's called something, it's called the leading coefficient test. So in a polynomial, p of x, g of x, f of x, whatever, that leading term, thank you, sweetie, is all that we care about. And if you remember, the leading term is the term that has the biggest exponent. We can tell end behavior just by looking at that, okay? We look at two things. We look at the degree and the leading coefficient. The degree is the n here, and leading coefficient is the number standing in front of the x of the leading term, okay? What you look at for the degree is, are you even or are you odd? Okay, so even numbers 2, 4, 6, odd 1, 3, 5, and so on. Leading coefficient is, are you positive or are you negative? Those are the two things that will tell us what happens with the arrows on the end of the graph. So our first two examples here are when your degree, give us this, is odd. How do I know so quickly? Well, I'll tell you that whenever you have end behavior that goes in opposite directions, one is up and one is down, that's going to be odd degree. So you can think opposite. Okay, so then how do you tell if it's going like this one, which is down, up, or this one, which is up and down? And that has to do with the coefficient sign. If the coefficient sign is positive, it's going to start down and up, right? Down, up. This is dotted in between because that's going to change. Whether it's a 1, a 3, a 5, a 55, the graph, all the points in between the arrows will look different from graph to graph to graph, but the ends will always do the same thing, okay? And a negative coefficient when we are up to the left and down to the right. See how the ends are opposite. Guys, there's a very famous graph called a line that you guys all know a lot of things about, okay? In a line, like if I just make up one right here, one thing you could tell me without having a piece of graph paper is you could tell me what this graph really looks like. You should be able to tell me that this is a linear function because it's odd, x to the first, which is odd, and it's got a positive slope. So you all know that a line with a positive slope rises left to right. I think we know that. Well, all odd numbers, whether that's a 1, a 3, a 53, the ends will always do the same thing. So anytime, and I'll show you what I mean when we get to an example in a second, but anytime it's an odd number with a positive in front, I just think, oh, it's just like a line with a positive slope. The ends are going to do the same exact thing. Same thing over here. If I just change that 2 to a -2, you immediately should know that your graph falls left to right. A line with a negative slope would go like that. Same thing here. Look at your ends. They are doing the same exact thing. Rising to the left, falling to the right. What happens in between, you can clearly see, is different, but it's the ends that are the same. Okay? So, being obnoxious, if I gave you this problem right here, you would be able to tell me exactly what the ends are doing. You'd go, this is odd with a negative. That's like a line with a negative slope. So it's just the end behavior of this graph is the same exact as this graph right here. A line, odd, with a negative slope. The end behavior of this rises to the left, falls to the right. Okay? So that's what we're learning. Those are harder to remember, to be quite honest. These are the easier two. When the degree is even, we go in the same direction. Up, up, or down, down. You know what I did there? Yeah. So if it's up, up, your coefficient is positive. If it's down, down, your coefficient is negative. There's a very famous graph that you guys know maybe not as much about as you do lines, but it's called a parabola, right? If you have a parabola with a positive number in front, it's concave up. Remember that? That's an even with a positive. A parabola with a negative in front of it is concave down, just like all even number with a negative in front, okay? So back to being obnoxious, if I gave you this, you would say, okay, this is even. That's like a parabola. And a parabola with a negative in front opens down, so I know the end behavior of this graph would be down, down. Okay? So let's put it all together in our very last example. I'm almost done talking at you. Okay? Let's look at example 1. Yeah, we haven't even gotten to an example yet. I told you it was a little bit longer. But remember, no new notes tomorrow. Just finishing today's homework and doing more practice. Okay. So, all right. We're not using a calculator. We're just going to sketch a graph. So let's pull out some information, okay? Everybody, here's where I'm going to bring back some other things too. Okay. Degree is 3. Find your leading term. The degree is n. That's 3, which means it is odd, right? Our leading coefficient is -1. That's what's in front of it. Of course, what we care about with that is that it's a negative number. So we just care, are you even or odd, positive or negative, okay? What that tells me is it's like a line with a negative slope. If I have a line with a negative slope, it would look like this, right? A line, odd, with a negative slope would go like this. So that means the end behavior of this graph is going to start up and down, just like a graph of a line. All right, so what that means is as the limit as x approaches -infinity, that's going to the left. What is our y value doing? It goes over here. It's going up, which is towards positive infinity. As the limit of f of x as x approaches positive infinity, that's my right end behavior. In this graph, going to the right, we're going down. How many turning points? 2. Remember, that's your degree minus 1 gives you your turning points. You could subtract one more and find your points of inflection, but we're not talking about that. And here we're going to just sketch the graph, okay? We should have 2 turning points starting up, ending down. Everybody's graph could look slightly different because where are we turning around? Who knows? What are our intercepts? Nobody knows. We don't care, okay? But we start up. I'm going to turn somewhere else, and down. So you can see my end behavior is just like a line with a negative slope. What happens in between is different, of course. Lines don't have turning points. All right, last one. Find your leading term. Remember, sometimes people don't do their job right, and they don't put it in standard form, the polynomial in standard form. So make sure you find the term that has the biggest exponent. It should be first, but you've seen it that it's not always. So this is a degree 4, which is even. Leading coefficient is 1, which is positive. Even is like a parabola, and if it's positive, parabolas open up, up, right? So when I see this, I think about this. That's what I see in my brain. So I know any graph that has even and positive is going to be up, up. So this is your left, this is your right end behavior. How do I know so quickly? X approaching negative infinity, X approaching infinity. They're both going towards positive infinity. Yep. Is the limit always what? That's a great question. I'm going to do the first homework problem with you, and I'll talk about it again. The order does not have to be left and right. That's why you want to read it carefully. You can put it in either order, and you'll see it in either order. Okay? Is that what you're asking? Right. Yeah. These, listen, with limit, you'll only see X here. The answer to a limit, what goes, like this is going to be the same every single time, okay? This is what changes. Remember, a limit, the answer, what's over here is what Y is doing when X is either going to the left or the right, okay? All right, how many turning points do we have here? 3. So I'm going to be obnoxious. I mean, you could make it look like a W, okay? But I'm going to just make it different because I want to make a point that it doesn't really matter where your turning points are, what your intercepts are. What we should have is 1, 2, 3 turning points and up, up, and behavior. But you could have done it like this, you know, as long as it has, whoops, that has way too many, sorry. But 3 turning points, up, up, okay? All right, let's go to the homework. I'm going to do the first one with you, which is kind of this on steroids. Yeah. I'm going to do number 1 with you. You want to do it with me too, I'm sure. Okay, so guys, number 1 is, let me write it. I don't have a blank copy, so I'm kind of writing stuff out. It's already factored for you, which is nice, okay, in some ways. So first question, this is going back to our last test. It's the zeros and the multiplicities. I don't need to see the work for the zeros, okay, but I'm going to show you the work because if I don't, I'm sure I'll get a question. Remember, to get zeros, you set your factors equal to 0 and solve. Can you do that in your head? Yes, okay? But there's something here I just want to talk about. When you solve this one, when I take the square root of both sides, I'm going to get 0, right? The square root of 0 is 0. And normally when we take the square root, we would put a plus or a minus in front of it. There's no such thing as a positive or a negative 0. 0 doesn't have a sign. But listen carefully. If you have a 0 here, and it was a degree 2 to begin with, that's going to count as a multiplicity of 2, okay? There's 2 solutions coming from this x to the second power, okay? So if this is x to the 4th, you'd have a multiplicity of 4, right? So that's the weird thing about that number. Here, this is x to the 1st. We have a multiplicity of 1, right? There's only one negative 3. Why is multiplicity important? Remember, it tells you how the graph interacts with the x-axis. When you are even, you bounce. When you are odd, you cross. And you'll see me do that when I sketch the graph here in a second. All right? So these are my zeros are your x-intercepts. We're going to have an x-intercept at 0 and an x-intercept at -3. That's what that means, and we'll graph it in a second. End behavior, limit statements. Limit of this guy is called f of x. And you can do left or right first. It doesn't matter. I always put left first. That's just my habit. As x approaches -infinity, okay? And I'm going to just set up my right behavior. The limit of f of x as x approaches positive infinity. That's going to be the same from problem to problem. I mean, the name could change, f of x, g of x, but that's how you always write left and right end behavior, okay? What comes after it is what the y values are doing on the left side and the right side, okay? How do we tell that if our equation is not in standard form? I need to know what the leading term is in the exponent. Well, this one's not too hard to like just distribute, but you really don't have to do all that. All you have to do is multiply each factor's leading term. So this is a factor, right? Like you factored out an x to the second, so that's x to the second. And then this is a factor. His leading term is x. If you just multiply those two together, you'll get your leading term. So this is odd, positive. I think line with a positive slope, it's going to go down to the left and up on the right, right? It's just like a line with a positive slope. So what am I going to put here? Positive or negative infinity? What's the left side doing? Negative. It's going down, right, on the left. On the right, it's going up. So when you go to sketch it, you have -3 and 0. There's the x-intercepts. You have to start down and end up just like a line with a positive slope. We don't know where the turnarounds are, so that doesn't matter. You could go up higher or lower, but you cross at -3 and bounce at 0. Remember, this is your even multiplicity. That's your odd. We cross at a 1, 3, whatever, bounce at a 2, 4, 6, whatever. Okay? Okay. I'll be around to help you.